Section 5.1, actually all of Chapter 5, is going to be our discussion of integers. And in 5.1, we're going to talk about addition and subtraction, and then in 5.2, we're going to talk about multiplication and division. There's not a whole lot new to talk about that we haven't already talked about whole numbers. So you're going to get some sort of sense of this looks a lot like what I've seen before, and that's going to be partly why. All right? So the first thing I want to talk to you about, however, is what integers are. So integers, any remembrances of what that means? How is that different than whole numbers? We talked about this a long time ago. It includes negative numbers. What kind of numbers? Whole numbers. It includes the whole numbers, which is 0, 1, 2, 3, 4, and on. And it includes now the negatives of those. So one way to write this. Okay, so I'm going to tell you what your book uses, but let me also show you what really is used. Your book is calling this I, which is, sounds really nice. Like, why wouldn't we call it I? That's not traditional math notation. I just want you to be aware that most places you see that referred to will be called Z, and it'll have a double line on it in the middle there, like we've seen that double line on the N for natural numbers. If you use I, it's okay. I don't want you to see Z somewhere written down and go, what in the world Z? Z is integers. It's Latin. That's why the Z is used. And so this list actually starts with the triple dots thing, right? You know, the what do you call it, an ellipses? Is that what it's called? I think that's right. And then we're going to go -3, -2, -1, 0, 1, 2, and then we're going to have that mirror image of the 3 dots on the right. So integers are all of the positive and negative whole numbers, including 0, of course, and it doesn't have a positive or negativeness to it. Okay. So we're going to talk about integer addition, and the first model is the chip model. All right, so the chip model looks something like this. So we're going to use the example 5 plus -3. So the first thing I want you to do is to draw a circular type shape circle. So inside of our circle, we're going to have chips. And our chips are going to have either chips that are positive or negative. Now I'm going to use this wonderful iPad device to make my chips have black and red. So if you don't have a red something with you, if you have any other color with you, call that red. Okay? So purple, blue, green, maybe you've got a crayon, I don't know. You guys have all sorts of fun stuff because you're elementary ed people, right? So find something in your bag that's got some kind of a color to it, borrow something from somebody nearby, but just remember that that color is the red that I'm using on the screen. Okay? This kind of model is usually done with actual physical, like poker chips. And in some cases, they're really nice because the poker chips are usually created so that it's one color on one side and the flipped color on the other side, so you can actually use them either way, and that's actually really friendly. You can sort of get double use out of them. But this black chip is going to represent a positive 1, and then when we do a red chip, it's going to represent a -1. So the chip model looks something like this. This says 5, so I'm going to do 5 black chips because that 5 is a positive. And then it says plus a -3, so that's 3 red chips. So I'm going to do 3 red chips. And this would be the image of the chip model. So if kids would actually get out chips, I mean these poker chip looking things, and they would do this picture. But then they would recognize, as you're hopefully recognizing yourself, that there's a way to simplify this. How can you simplify this picture? Cancel out. What cancels?
A red and a black.
Yeah, a red and a black chip add to be a value of 0. They combine to be sort of opposites of each other. So we have the ability to cancel out 3 of these because they combine to give us 0, which means that the resulting chip model, and if we were to draw the picture again, sort of in a circular point of view, all it would actually still have in it then is 2 black chips. So this ends up being the number 2, and you can physically move these objects around. That's kind of friendly. Okay? It's very hands-on, very concrete. And something that's really difficult for kids to grasp, this idea of negatives. I mean, like, they don't sort of look like they should even exist. I mean, how can you count something that's not there? It's a negative something. Well, where have you seen negatives that actually exist before? What's that?
Temperature.
Temperature. That's a good example, right? When we talk about negative temperature. And you could use either temperature scale to do that, right? The two most common ones, Celsius or Fahrenheit. Where else have you seen negatives exist? Okay, one at a time. What did you say, Carly?
Bank account.
Bank account. How in the world could that happen? You're not talking from personal experience, I can tell. So tell me how that could happen, Carly.
Well, if you run out of money and you spend over, you'll have negative amounts in your account.
Yes, you will. So if you overspend what's in your bank account, you overdraw your account, it will say negative. Yes, it will. What does that mean in terms of that, though? It means you owe somebody money. So maybe it's not even so much as you overdrew your account. Maybe you took out a loan, right? That's another way where that negative quantity matters. And children can understand this too because mom and dad let them borrow money to buy that pack of gum at the store or something like that, and they owe mom money. My son really gets confused about that because he'll show up sometimes and he'll have forgotten his dollar that he's supposed to have for tithe. We pay our kids money, and they have a give dollar every week. We don't do ratios at this point. They don't really understand that yet. And so however much money they get, they just give $1 of it. They get money, it's like $3 to $5 kind of monies. Okay, so they give $1 to Jesus every week. And so when my son forgets his give dollar at home, he still wants to give it at church. And he gets very confused when I pull a dollar out of my purse and allow him to put that money back in, because in his mind he already gave his dollar and he can't figure out why that dollar at home now belongs to me. It's really still a concept that he's struggling with, so we're still working on it. Okay, but this is this idea of borrowing money or something like that, right? So negatives are there. Any other negative examples you guys can think of?
Electricity.
So what about electricity?
Like negative charges.
Oh, that's true too. In fact, we're going to come up with a model. That's our next model. Did you see that already? Yeah, it is. Okay, the charged field model is another model that we used where we do have some negatives. This one looks almost identical to what you see on this one already. In fact, you don't even need the red or the black, although if you have them, it's fantastic if you want to use them. I will use that on my picture just to sort of accentuate that that's what's happening. You still use a circle. And what you do is you do a positive for a positive value. So when you put a number that's or when you put a plus there, it actually means positive 1. And I'll use red, although you wouldn't have to. When you put a negative, it means negative 1. So this is actually a pretty easy model to do. We're going to take 5 positives. And you're going to have 3 negatives. And just like on the last one, a positive and a negative cancel each other out. So we can mark out 3 sets of these because they sort of cancel each other out. And then we're left with 2 positives, which means the answer is 2. Okay, this isn't as physical, however, right? I mean, there's not actual chips involved. If kids were working with this, they would be working with pluses and minuses, which is more abstract. You guys don't have any problem with it, I get that. But with kids, the chip model is a little bit more concrete because there's actual physical objects when it's taught that way. Number line model is another popular one. You've seen this one talked about before as well. So what you're going to do is you're going to draw a number line. And it starts at 0. And it's going to go forward 5. Why 5? Because 5 is where we start. Wherever the first number is where you're going to start. So if it started with a positive number, you're going to go positive first. If the negative 3 had been at the front, you would have gone negative first. Okay, so you're going to actually go whichever one it is. And with the number line model, you'll see either arrows or, I'm going to draw it sort of circular. I can't remember if your book uses the circular ones or actual physical straight lines. I don't know, it doesn't really matter. But you're jumping from 0 to 5. That's what that 5 means. And then when you do the negative 3, you're actually going to go backwards 3. That's what the negative means, right? It means count backwards 3. So here's 1, 2, 3. So we're going to go backwards to here. And wherever we land, in this case, the number 2 would be our answer. So if you imagine, and I'm going to do it up here at the front of the room. So if you imagine you start on this side of the classroom and you move 5 desks forward. So we've got 1, 2, 3, 4, and 5. And then I need to move 3 desks backwards. So here's 1, 2, and 3. And what you're wanting to know is how far am I away from where I began? I'm 2 desks in. Okay? So you can actually do that with a physical model as well. It doesn't have to be a number line picture point of view. Children could actually step out what I just did and have that sort of a sense of how far away am I from where I started. So the number line point of view. Patterns is also another one that's very interesting. not going to appeal to every kid. None of these appeal to every kid, but let me show you how the patterns model works. So the patterns model works by taking what we know about addition and showing what would happen when we actually do this with this idea of addition of negatives. Okay? So what we're going to do is we're going to start with taking what 5 plus, we'll do starting with the number 2. There's nothing special about 2, but that's what we're going to start with. So 5 plus 2 is the value 7. Okay? And instead of adding 2, now we're going to look at adding the number 1. 5 plus 1 is the number 6. And 5 plus 0 is the number 5. And if you look, we've got 7, 6, 5. There's a pattern here, right? So if you take then and talk about 5 plus the number -1, which is simply 1 less than 0, then the number by the pattern on the right should be the value 4. Not because I added 5 plus -1, but because I looked at the pattern 7, 6, 5, and the next number in that pattern should be the number 4. And then you can do the same thing and continue down. So we'll just go with -2 now. Well, 7, 6, 5, 4, this should be 3. And if we do it again, because that's where we're actually headed, was supposed to be 5 plus -3. 7, 6, 5, 4, 3, the answer then should be 2 by a pattern of what was going on based on the addition fact of positive numbers that we already knew. Okay? All right, another thing in this section is the idea of absolute value. You guys have seen absolute values before. I would like for you to think about what you remember about absolute values, because what you remember is probably only sort of a partial picture. So tell me, what do you remember happens when you put these absolute value signs on something? What happens? Okay, so it changes a negative number to a positive value. What does it do with a positive number? It stays the same. Okay, so this is a good description. It's a good place for us to start. So it does one of two things. So the first thing that you told me, Carly, is what happens when the value is negative. So if you have a value that's negative, what did you say that it does? It changes the sign, right? So it changes it from being negative to being positive. Well, the way we represent changing signs is we represent it as a negative x. And I know that feels really awkward, but think with me. This first line says x is already negative. So pretend it's a number, -7, okay? So if I have a -7 and I multiply it by another negative, what happens? I get a positive. This looks really awkward though. I mean, doesn't it? I mean, it looks like this number is saying that it's negative. It's not. It's saying I want the opposite of whatever the value was before. And this condition over here tells me the number it was before was a negative number. So when I take the opposite of a negative number, that is the positive number we started with. The other option then is that the number was already bigger than 0, and actually we'll throw in the equal to 0 here as well. And so what happens when we take the absolute value of a positive number or of 0? It stays the same, right? It doesn't change at all. So the absolute value of 7 is 7. Whatever the number was, it stayed the same. And this is all well and good, and this is sort of an algebra picture of what's going on. However, there's a very simple number line picture that makes a lot more sense. So let me talk about it from that perspective. Here's the number 0, okay? Everybody good with that? If I want to talk about the absolute value of x, what I'm actually talking about is I'm talking about the distance away from the number 0 is x. It's a distance. So right here, or right here, if x is positive or x is negative, right here's distance would be the same. Both of these distances would be the absolute value of x. It's a distance argument. It's the same reason that when I say, how far is it from here to my house? I'm going to do it in terms of minutes because I don't know exactly the miles. It's 20 minutes. But I don't say that from my house to here is negative 20 minutes. We don't talk about it like that, right? We don't talk about distances or even times really very much in terms of negatives. We talk about them in an absolute value sense, right? So what I want you to see is what happens then when we're looking at some examples of these. So we're going to classify these as true or false, and if it's false, we're going to show a counterexample that makes it false. So things that are going to make things false or whatever, what you want to be thinking about is what happens when these negatives get involved, okay? That's what you're sort of thinking about. All right, so take a look at the right-hand, let's start with the left-hand side of the first one. This one says the absolute value of x squared. So what happens when we put absolute values on things? It makes them positive. So whatever happens on the left-hand side, it's a positive number, correct? Because it says absolute value. Or it could be 0. Let me clarify that. It's a positive number or 0, because the absolute value of 0 would also be 0. So if x were 0 in this case, it would be okay by default, right? So it's a positive number on the left-hand side. What about the right-hand side? It's got to be positive. Why is the right-hand side of this first one always positive? Because it's squared. When we square numbers, they are always then positive, right? Even if the number was negative to begin with, when it gets squared, a negative times a negative is a positive. And we're going to talk a little bit more about that when we get to section 5.2. But you guys remember that fact, right? When we square things, they become positive. So this is actually true because both, not that it asked for a reason why, but I want to write it down so that you guys have a reference point. Both sides are positive. Or 0. I should probably say that specifically. Or 0. 0 would be fine too. We could have both sides equal to 0. If x is equal to 0, by default, we get this to be true. How about the second one, part B? How is part B different than part A? It's cubed. And why or how are cubes different than squares? They can be negative. If you take a number that is negative and multiply itself by itself 3 times, right, like negative 2 times negative 2 times, negative 2, you actually get a negative. It's a negative 8 in this case, but it's negative. So that can happen when we have something multiplied together an odd number of times, okay? So the left-hand side, which has the absolute values, what can we say about that side? It's always positive. But what can we say about the right-hand side? It could be negative. And in fact, the example that I just wrote down would be an example where that happened, wouldn't it? So if we let x equal to negative 2, then the absolute value of negative 2 cubed would be, in fact, let me write it this way. We're looking at seeing whether or not they're equal. On the right-hand side, we just said that was negative 8 already. On the left-hand side, what would it actually be? It would actually be 8, because we have to take the absolute value of the negative 8 when we're done. So if you want to do it this way, you can think about it. This would then be 8. So this is not equal. I mean, could it be the same? Sure. What kinds of numbers would actually make this statement true? Positive numbers or 0 would work too. So there are numbers that would make the statement true, but just not all numbers, right? How about part C? It says absolute value of x is not negative. Is that a true statement or a false statement? This is false right here. Is that true or false? It's true. The absolute value of x is not negative. How is C different than D? One says not negative, the other says positive. Why are they both here? Are those my only options? What's missing, Katrina?
Neither.
It could be neither. What number is not positive and not negative? 0. 0 is the number that gets left out of this argument, right? So the absolute value of x has 2 options. It's either positive or what? Or it's 0. But it legitimately could be 0. I mean, that's a legitimate answer. So it isn't ever negative. So part C is true. It is not negative. But part D is actually false, because x could be 0. And then the absolute value of 0 is 0, and 0 is not positive. It's the only counterexample, right? Everything else would work, and it would be positive. But this number is the one case where it doesn't work. All right. We have seen these before. Properties, properties, properties. We've seen them at least twice. So here's our third exposure, I believe, to properties. But now they're properties of integers. These four we have seen before. They're nothing different. So the first one is closure. What does closure mean? This is the one you guys still struggle with, I know. What does closure mean?
You have a set of numbers and only those numbers.
Okay, so you have a set of numbers. In this case, our set of numbers are integers. Okay? So remember the description I keep talking about. I think Katrina's looking around in the upper part of the room because that's how I've described it. That's what we're going to pretend. So imagine they're floating around on the top of the room. All the numbers. Positives and negatives and the number 0. They're all floating in here. Closure means you have to be able to take a number and another number, and they could be the same number, but you have to be able to take two numbers from the room and combine them with whatever operation you're working on. Okay, in this case, addition. So can I add two integers together? And if I do, will I get another integer? And the answer is yes, I can, and yes, I do. So if I add two integers together, I always get another integer. I don't get, say, a fraction. Right? Integer plus integer is integer. That's what closure means for integers. That's what closure means in general, except that we have defined that the numbers floating around in the room are the integers. So closure property of integers says that if you have it says up here, integers a, b, and c, then a plus b is a unique integer. The fact that it's an integer is the part that's the most important. It is unique. It only gives you one answer, but the fact that it's an integer is important. We talked about sets where that doesn't happen, right? Odd number plus odd number doesn't equal odd number. That doesn't always work, right? But there are some that do work. You know, an even integer plus even integer does equal an even integer, something like that. Commutative, what's commutative property? You flip the order, right? You commute the order. So the commutative property says that if I have a plus b, it's the same as doing b plus a. Right? So 5 plus 3 is the same as 3 plus 5. And it works with negatives too, right? I gave you an example with whole numbers, but if you had 5 plus negative 3, that's the same thing as negative 3 plus 5. What's associative property? It has parentheses, and in particular, it's the grouping of how things are grouped within the parentheses. So if you have a plus b plus c, and you have the first two numbers grouped together, it will be the same thing as if you have the a plus b plus c. The order doesn't change, but the second two numbers are grouped together instead. It worked for whole numbers. It worked for natural numbers. It will work for integers as well. Identity property. Some of you are still working on tests that talk about identity property from chapter 3. What is the identity element for addition? 0. It is for addition of integers as well. Any integer plus 0. Okay. So any integer plus 0 on either side, so a plus 0 or 0 plus a, is going to equal a. And it works for negative numbers. We already discussed it working for positive numbers. It works for negative numbers as well. So if you have negative 5 plus 0, it's negative 5. If you have 0 plus negative 5, it's negative 5. But we have a new property, and this is the first time we have had this property because we needed negatives in order for it to exist. This is the additive inverse property. The additive inverse property says that for every number, you have another number that you can add to it that will give you back the identity, in this case 0. So you guys know this. If I took the number 7, what number can I add to 7 to get back to 0? Negative 7. If I took the number negative 400, what number do I add to negative 400 to get back to 0? Positive 400. That's the inverse property. We didn't have that before because we didn't have negatives before. So this is saying there exists a unique number negative a, the inverse or additive inverse of a, such that a plus negative a, and it has to work on either side, equals negative a plus a equals 0. So a number and its inverse have to add together to give you back the identity, which is 0. Now there are 3 more of these that are in theorem form down here that we're going to work on. The opposite of negative a is positive a, so when you talk about a negative times a negative equaling a positive, that kind of an idea was present here. Part B says if a excuse me, is equal to b, then a plus c is equal to b plus c. So you can add a number to equal numbers and they will be the same. So 100 plus 3 is 100 plus 3. And the third one is probably the most helpful. It says if you have negative a plus negative b, it's the same thing as having negative of a plus b. So that one's the most helpful probably, is this idea that if they're both the same sign, then we can combine them and keep the sign. All right, that's it for addition. Let's take a look at some subtraction properties. Definition of integer subtraction says the following. For integers, the word right, for integers a and b, a minus b is the unique integer n such that a is equal to b plus n. And we've worked with this definition before too. We've talked about the fact that oftentimes children are taught to subtract by doing something like this. They're saying, in fact, we'll use numbers even. Let me use numbers. They're taught to do something like this. 7 minus 3 equals question mark. And instead of working with 7 minus 3, they say 3 plus what equals 7. Right? Kind of what's missing to give them that. That's one of the first ways that kids are taught to think about subtraction, is this idea of a missing part or missing piece. And we talked about a missing add-ins model for subtraction before. Very much the same idea. We can work with CHIPS models for this as well, and that's where we're headed next, is to do the different models. And another thing, this theorem right here, sorry, this is sort of in the wrong spot, but theorem 5.4 that says for all integers a and b, when we talk about subtraction a minus b, it is equivalent to talking about the addition of a negative. And that's actually really helpful because we have a whole bunch of stuff we already know about addition properties. And so now if we can change subtraction so that it looks like addition of negatives, we can talk about it in much the same light. All right, let me show you the CHIPS model idea first, and then we'll stop and we'll pick back up here next time. All right, so we talked about the CHIPS model before, the idea that we have these different chips, and one chip is going to represent positive, so I have positive 5. And then I've got the one chips that are going to represent my negatives. So there's my negative chip, and it's red. Here's the problem. When we're modeling this, this subtraction sign right here means to take something away. The problem is that I do not have 3 negatives to take away. So this is saying take away 3 red. There aren't 3 reds. Somehow I've got to have 3 red to take away. So here's how I get them. I put my 3 red in along with 3 black. Those just cancel, right? I mean, I didn't really change the fact that the inside of that diagram is still the number 5. Do you guys agree with that? What's inside there is still the number 5. But the way that I mark that I take things away then is I'll circle those 3 red and I'll draw an arrow out to indicate that I'm removing 3 reds. Remove the 3 reds from the account. So it would be like going into that spreadsheet that had that negative bank account and simply hitting delete on that. Well, everything changes, right? Everything changes based on that negative being gone. And so what ends up being left then, if you count them, is there are actually how many black chips left in your diagram? There are 8 black chips left in your diagram. They're a little bit bigger this time because I drew them funny. But this is actually the number 8. And this gives a very concrete picture then why 5 minus negative 3 turned into 5 plus 3. Because that's what happened. But we never said it. We did a model with chips that showed it.